unprompted. Yeah, we just started. Yeah, they'll join online. The man is not in office yet. Don't jump.
Yeah, maybe you can get started. Yeah, thanks so much for coming either in person or over Google Meet. Today's my pleasure to have Ari presenting random samples. Ari is a senior principal software engineer at the Red Hat AI innovation team. He works on different aspects of coding agents. Specifically, he works on building evaluation infrastructure for coding agents. Before joining Red Hat, Ari was leading AI for code efforts at both Google and Meta. I think Ari is one of the few people who started working on coding agents before it became a big topic nowadays. Personally, I feel like, Ari was Red Hat last time a year, but I feel like he thinks like he built for me like a long term, like a
born Red Hatter.
Yeah. So, because I really have so much to share. He has a lot of experience on coding agents, and I really learned a lot from him. Today, Ari is going to talk about some of his recent effort on coding agents and specific on scaling training and evaluation data for coding agents with Sui Benchify. So without further ado, yeah, please take it away.
Great, thank you so much, Hal, for the introduction. And I know most of the folks here have good context on coding agents and evaluating them, and also SwiBench, which is kind of an important prior art that I'll be talking about. But I'll try to give a little bit of background just to motivate the problem that I've been working on for the past couple months. Yeah, so can everyone hear me okay?
Yeah.
Okay, awesome. Yeah, so like Hal mentioned, I'm a software engineer on the AI innovation team. I studied machine learning at Columbia University. I have a background in ML developer tools. I've been working in this area for a while now, since actually before ChatGPT. And I work from the West Coast in the Portland metro area. And I'm interested in improving how we measure and optimize AI agents for coding. So I think before we dive into kind of the technical details, I want to talk about why benchmarks and training data matter for coding agents. I think that the value of coding agents is pretty clear at this point. The practice of software engineering has been pretty amazingly transformed by technologies like Claude Code. And at the same time, organizations are trying to figure out how they can get the benefits from these models while enabling cost performance optimization. With so many choices in terms of the models and the harnesses, organizations are also needing to answer how we can go beyond vibes-based measures of how good different models and harnesses are, and to truly be able to measure the strength of different coding agents for different tasks. And I think there are tons of efforts in public literature and public benchmarks trying to measure the performance of these agents, but there's also a significant contamination risk, meaning that when we come out with a public benchmark like SwiBench or Program Bench, Feature Bench, Terminal Bench, as soon as it's published, that data is out there, and the solutions to a lot of the problems can get baked into the training data of frontier models, both open source and proprietary models, which makes it so that the results that they report on these benchmarks are often unreliable, and it's hard to say that good performance on SwiBench from a model like Kimi really is going to translate to actual strength in terms of real-world performance. So that motivates the need to have a renewable supply of fresh and realistic problems. Beyond evaluation, having training data for coding agents is really important if you want to do model and harness training, and notably the bug fix data that you would need in order to do large-scale model and harness training is pretty scarce and expensive to curate. And we'll go into exactly why that is in a little bit. For this training data, part of the motivation for my work is the idea that synthetic data can help fill the gap from real bug fix data that's hard to curate. So diving into this SweBench, most of you have probably heard of SweBench. It's kind of the standard for evaluating coding agents, and most new models and harnesses that are coming out will report their performance on SweBench, and also a subset of the problems in SweBench called SweBench Verified. How this works is essentially that coding agents are asked to take an issue description and a Git repository, and to take that issue description and to turn it into a patch, and a patch that is going to be tested on whether or not it passes human-written tests. And so to break this down, I have an example that I pulled out. So this is an example pulled from the SweBench benchmark. And as you can see, it's an issue in the Django repository. SweBench is comprised of examples from 12 Python repositories like Django. And the problem statement, query set ordered property is incorrect for group by queries on models with meta ordering. So the model is given this issue description. And in the benchmark, the issue is linked with the patch that fixes this issue. Let me see if I can zoom in, because this is probably a little bit small. Can everyone see the text?
Yeah, I think so.
Okay.
Yeah.
Yeah. So for this patch that has been linked to the issue from the previous slide, the patch gets separated by SweBench into a gold patch, which is the feature code, and the test patch, which is the unit tests that exercise the feature code. And notably, in the benchmark, this is all human written, or agent written if a human is driving the agent. But this is kind of pretty important to be able to take the sample and to break it apart into the feature code and the test code. And the expectation of the code that the agent is going to write is that it's going to have the same functionality as the gold patch on the left, and that it's going to pass the human-written unit tests annotated as the test patch on the right. So this SweBench benchmark came out of Princeton in 2024. It took 3 years of collection effort, utilizing the time and effort of expert software engineers to curate samples that could be appropriate for the benchmark. And ultimately, they ended up with around 2,000 instances and around 500 high-quality instances. So a small number of repos, a single language, a lot of collection time and effort, and a fair number of examples that came out. So and feel free to stop me at any point if folks have questions. The reason that this takes so much time and effort is that actually most issue patch combinations don't qualify as valid SweBench instances, and they need to simultaneously satisfy a set of around 11 independent constraints in order to be valid for SweBench. In particular, it needs to be a bug fix. A lot of patches are going to be refactors or features without unit tests, or maybe documentation changes, and those don't qualify as valid examples for SweBench. In order to be objectively measurable, there need to be unit tests that come with the features, and the unit tests need to basically fail before the feature patch and pass after the feature patch. In addition, the PR has to be linked to an issue. The diff has to separate cleanly into feature code and test code. Tests need to fail before the fix and pass afterwards, and so on and so forth. So ultimately, like, the conjunction of all of these constraints makes it so that less than 1% of PRs end up as valid instances, even when you look at a well-maintained repository with good unit test coverage. And like I mentioned on the previous slide, the original SweBench took actually 3 years and only covered 12 Python repositories. So Kai initially had this idea, and the motivation was like, can we basically turn any GitHub repository into a set of SweBench compatible problem instances automatically? And can we use AI to scale the curation process and basically do PR mining at scale in order to be able to identify patches that can be good samples that are compatible with SweBench? And that led to Kai's work on SweBenchify, which in the first version was an agent-based solution, which would go and look at a repository that you pointed it to and build a Docker container, kind of identifying the dependencies and the toolchain for the programming language used in this repository, and then would work to go through the commit history and the issue history to find issues that are linked to pull requests, and to filter those down to ones that can be compatible with SweBench. And it kind of separated into these different phases, collecting PRs, filtering and extracting them, separating the patches linked to the issues into gold patch and test patch, going through Docker validation, this F2P, P2P thing, fail to pass and pass to pass, and then doing flake quarantine, since even if a unit test passes once doesn't mean it's going to pass consistently. So what worked well about this is that we were able to get multi-language support, which extended the original SweBench idea, which was Python only, to be able to cover other programming languages, and especially ones like Go, which are relevant to our work here at Red Hat. We were automatically able to do problem validation using Docker to measure the tests that are failing before a certain patch and passing after the patch. With flake quarantine, we were able to automate the environment discovery using AI to essentially discover how to do all of the toolchain and programming language dependency setup for these repositories at different commits. And most importantly, perhaps, this helped us address this issue of contamination, where having the problem where as soon as you post a public benchmark, the answers get into the training data of these frontier models. It's a good way to fight against that, to basically be able to generate or mine PR data on the fly in order to be able to produce new samples. And we did some experiments that showed that when we do PR mining for recent issue PR pairs, that we didn't see a contamination effect, which was good. What didn't scale was that the yield of less than 1% of the PRs made it so that basically the number of problem instances that we're able to get out of any given repository is going to be pretty low. There were a number of issues around commit reachability and around issue quality as well, making it so that most of the PRs that we were looking at didn't qualify as proper samples. And so from here, I think we started to think about, well, what could we do to increase the size of the benchmark, the number of instances that we're able to derive from the repositories that we're looking at? And that led us to look at synthetic issue PR pair generation. Again, this sort of dives into some of the hand-wavy math around why most issue PR pairs fail to convert. And it's essentially that they have to fulfill all of these independent constraints. And when multiplied together, it ends up with quite a low yield. So with synthetic data, instead of mining real bugs, if you synthesize them, oh, sorry, was there a question?
No, Kais is getting excited, and yeah, he just said very clever.
Cool. So with synthetic data, you can eliminate all of like 6 of these 11 constraints right off the bat. By synthesizing the issue PR pair, you can create the bug, meaning that you're sure that this issue PR pair is going to be kind of like the appropriate kind of patch. Patch separability, if you're synthesizing it, you know from the get-go how to separate into gold patch and test patch. Decontamination isn't an issue, or contamination isn't an issue since you're synthesizing these fresh. And so a lot of the issues that we ran into, which made getting a good problem instance yield from mining GitHub repos, go away when we look at synthetic data. But synthetic data is often not going to be, well, let's just say that there are questions when you're generating synthetic data, which is like, does your synthetic data match the real distribution and qualities of the real data that we're mining? And so questions that came up for me were, are the synthetic bugs realistic enough so that basically they pass an LLM as judge test, being able to discriminate them from real ones? And also, are they difficult enough to produce meaningful separation between frontier models? And maybe a last question that I had is like, okay, if these are difficult problems, and if they are realistic looking, are they going to be good for training as well? Are they high quality in the sense that they're samples that frontier models and harnesses can learn from? So we weren't the first folks to think about this idea of generating synthetic SWE-bench compatible problem instances. At NeurIPS in 2025, there was this great paper called SWE-Smith that used a combination of LLM methods and, Giorgio, do you have your hand up? Oh, just stretching.
That's good. Oh. Sorry. Actually, I have a quick question.
Yeah.
Like in this synthetic data slide, in the previous slide, did you also explore like finding to increase the yield, picking the ones that, say, for example, don't pass trivial one of these and then fixing it with some LLM? Like turning an existing one to pass more of these criteria.
Yeah, that's a great idea and something that I haven't explored, but could be a really nice future direction, doing kind of like a hybrid mined and synthesized sample.
What is Abhishek's first contribution to the project?
There's also like a lot of work around bug finding in the literature, and kind of a similar thought or curiosity that I have is if you could get good problem instances, instead of by looking for linked issue PR pairs, just go find bugs in the wild and then enrich those bugs by coming up with corresponding problem statements for them after you find them. So I think definitely there's opportunity to explore kind of some of these hybrid strategies as well. Okay, so SWE-Smith, in terms of their synthesis, they had a few different strategies, which were LLM based on AST mutations, and then a small number of samples which were similar to what we were doing with mining, that they called PR mirror, which was reversing real PR patches, which they found actually to be most effective for training, which was interesting. So Sweesmith's primary goal in their paper was to be able to generate a large number of instances for model and harness training. And they were able to show that they were able to take a small model, and by generating these 50,000 instances for training a harness for that model, they were able to improve their performance on SweBench verified, which was really cool to see. So this is a Sweesmith example. And I think that this can be good motivation to look at, because I feel like it points to what I think is wrong with Sweesmith. So the problem that they come up with, which is synthetic, is that their AST mutation takes this violation class in Flake 8, which is a Python linting tool. And the bug that they introduce is randomly removing the base class that violation inherits from. And their automation, they take this AST mutation that they produce and feed it into an LLM. And the LLM takes it and comes up with a corresponding problem description. And the problem statement that they make is that the violation class breaks when not inheriting from named tuple. And they go ahead and describe it and how the behavior and expectations change when you do this kind of silly thing, which is to randomly remove the base class. And so I would argue that this is kind of silly. Like, as a challenge for a coding agent, like a real software engineer is quite unlikely to randomly remove a base class. And then, I mean, even if you agree that even if you don't question whether this is a realistic bug, certainly like the issue title and description make it so that this is not a realistic bug. Like the issue title in this case literally gives the agent the solution. It tells it like what broke, how it broke, and exactly where it should look in order to make a change to fix it. So I think that it's pretty clear in this case that this real example from the Sweesmith dataset, it's not realistic and it's not difficult, which should make us think like maybe this is not a good sample for evaluating coding agents, for making decisions about which coding agents and harnesses are stronger, their relative strengths, and that it might not even be a good example for training either. Just to elaborate, I think the issues that I see with Sweesmith are that there are realism gaps, no quality gates on mutations. Basically, anytime that Sweesmith is able to come up with a mutation that breaks at least one test, it passes and is included in their data set. And then, importantly, the issue that we saw and other issues in the Sweesmith dataset are describing the mutation that they generate rather than a symptom. If you think about GitHub issues or issues in any software tracker, oftentimes it's users reporting symptoms like I ran into, I was unable to do this thing and I'm not sure exactly why, but this is kind of a description of what I experienced when using this software. Whereas in the Sweesmith generated issues, basically they're asking an LLM to turn the mutations that they generate into kind of exact diagnostics for what changed. And this removes a lot of the challenge from the model that's trying to do the reverse engineering of taking the issue and trying to get back to the gold patch. This also points to difficulty gaps where localization is trivial. Oftentimes the issues are telling the model exactly where it has to go look in order to make a fixed patch. And in addition, because there's no quality gate on mutations, oftentimes there are catastrophic breakages where a single mutation will break dozens or hundreds of tests. In some examples, it was like several hundred tests broke with a single change in the SweSmith dataset, which I think is not super realistic to bugs out in the wild. So ultimately, our hypothesis is that SweSmith problems are too easy and too obviously synthetic to serve as meaningful eval benchmark. So this motivates the second iteration of SweBenchify, which was to take kind of a similar approach to SweSmith, but to add a couple of important differences to increase the difficulty and realism of problems that we're synthesizing. So first off, we do target selection, where we go through the functions in a target repo and rank them by test coverage, and also look for edge case and complexity signals in order to be more targeted in terms of looking for complex functions to introduce mutations into. In addition, after target selection, after we find a function that could be good for introducing a bug, or a set of functions that could be good for introducing a bug, we do validation. Whereas SweSmith just requires bugs to break a single test, we run the full SweBench validation, including computing the fail to pass and pass to pass ratios, and reject changes that break more than 5 existing tests, ensuring that the test patch, and ultimately ensuring that the test patch doesn't reference names introduced by the gold patch. There's an issue generation information firewall, where instead of just feeding the mutated code into the issue describer, basically we take the code level bug and strip all of the technical details via an LLM, outputting a single sentence that might be something like, the last item in a collection is not processed. And then the issue writer doesn't get to look at the solution, which could cause an information leakage, but just looks at this single sentence summary of the bug, as well as the test output from this compute F2P, in order to come up with an issue description. And this basically ensures that none of the information about where to look for the bug, or kind of specific functions or classes that might be involved in solving this bug, all of that information is removed from the issue descriptions that we come up with. And then ultimately, to ensure a level of realism, we use self-screening, where in the synthetic data generation process, we use an LLM as judge in order to filter out problem instances that the discriminator classifies as high confidence synthetic. So we have a few different steps to ensure that the problems that we're generating are going to be both realistic and challenging. You have your hand up, question?
Yeah, quick question. Can you elaborate a little bit more on how the single sentence, like the last item in the collection is not processed, can help with the issue generation? Maybe a simple example.
Yeah, definitely. So in both SweSmith and SweBenchify, an LLM is used to transform the code change, or the bug that was introduced in code, into a corresponding issue description that should describe, or basically be the problem statement for the model or harness that's trying to solve this benchmark problem. But the difference is that instead of having the LLM that's writing the issue description be given the code patch, we have basically like an information boundary, where we have one LLM step that takes the code mutation and produces a single sentence summary. And that's sort of like a lossy mechanism, where now the thing that actually ends up writing the issue description doesn't have access to the code that was changed, just kind of like a a short summation of what a short natural language summation. And the theory here is that that makes it so that the LLM writing the issue description is less able to give away code level hints to models that are working on this problem, because it doesn't have information about basically like what the mutation was, which file it was located in, what function or class might have been changed. All of that has been filtered out. And the issue writer in Sweet Benchify case only has this kind of short summary of what was changed as in natural language, as well as the raw test output from the validation that we did. Does that make sense?
Makes sense. Will this also introduce some hallucination that the issue generator take the lossy information and making things up?
Yeah, I think that it could. I'm not sure the extent to which this is a problem in practice, but you can certainly imagine that that could be an issue where maybe, since it is kind of like a lossy filter, that we might lose key information that's needed to come up with an appropriate issue description. So I think there's potential for that to be a problem, and we would need to do some analysis to gauge the extent of that.
But just quickly, why do you think hallucination is a problem? You're cutting down, no? You're not increasing context. I mean, like, it's just want to understand, like, where is that concern coming from? Hallucination on which part?
I mean, for example, the summarization is condensing the context into a very, very short summary, and then the issue generator is trying to inflate it. During that thing, I think it is possible to add something that may be not accurate.
You mean the inflation part, right? Like,
yes. We are trying to gate the issue generator from accessing the actual patch by giving a summary. And when the issue generator is trying to reinflate that compressed information, it is possible to introduce something that is not true.
Yeah, it's definitely possible. I think that what we would see if that was a big effect was that in our synthetic data set, we would end up with a lot of problems that were kind of like unsolvable or too hard, or basically no models and harnesses would be producing patches that pass the tests for them. And then ultimately, we didn't end up seeing that that on most of the problems that we generate, they are solvable. So I think it's a super valid concern, but I think that the data suggests that in practice, it's not a big problem. So a couple of last important differences. SweetSmith uses a fixed template for issue generation, like the kind of like the natural language, for the issue that ends up being written in SweetSmith. There's a fixed template, and by contrast, our approach is to look at the target repo that we're trying to generate issues from, take a few real samples mined from the Git history, and give them to the LLM that's writing the issue description to provide them as examples that allow the issue writer to match the style, structure, and tone in the samples that we provide. And we have a few measures correspondingly that make our issues look more realistic to kind of like an LLM as judge to pass the self-screening, which are randomizing the opener styles. They can be different tones like frustrated, casual, terse, and so on. injecting social artifacts mined from the Git history. So a lot of our issues that we generate will end up mentioning certain contributors or referencing related issues from the Git history to increase the realism. And in addition, we'll have different artifacts like tracebacks for errors that get humanized by having them formatted similarly to the samples that we mine from the Git history. So in contrast to the Sweetsmith example that I showed earlier, here's an example coming out of Sweetbenchify. And this is from the kind of like RPC protocol library, gRPC, the Go bindings for gRPC. And the problem statement that we come up with is that connections should be rejected at creation time, missing credentials, conflicting transport security options are being silently accepted, tests that expect an error on new client without creds are passing through without one, then leaking Go routines. And so this is pretty cool, where you can see that this is actually describing the symptoms that a user running into this buggy software would experience. It's not describing the solution. It doesn't give any hints about where the solution should be applied, or like any code level hints about like certain functions or classes that might be involved in fixing the problem. It just describes that connections that should be rejecting are being silently accepted, which is realistic to something that a user might face. The gold patch is on the right, and what's kind of cool is that this isn't just a simple AST mutation that is the fix. It's actually kind of like a subtle ordering issue, causing connections that should be rejected to be accepted. And so this is a big improvement. I briefly wanted to mention, because I used Remote Factory pretty heavily through the development of the synthesizer, that Remote Factory is a caches project, and it's one of these cool software factories. And what kind of differentiates it from a lot of the other factories that I've looked at is that it's really focused on this kind of like autonomous loop idea, where you give it a problem to work on, it comes up with hypotheses for how to go and solve it or improve your score on this problem, and it goes through this build and evaluate loop, ultimately only keeping changes that improve the score. And for the work in having Remote Factory improve the synthesizer of Sweetbenchify, I had two ways of evaluating the synthesizer, which were, number one, how realistic are the bugs that are being generated, and I used an LLM as judge as a discriminator to basically classify, is this a real bug, or is it kind of like a fake synthesized one? And then also the difficulty, where I wanted to not only be generating realistic bugs, but I wanted to generate bugs that could create good separation between frontier models. And so I had a measure that, in addition to measuring the kind of the judge evasion, also measured the kind of like the variance in performance of different frontier models. I was mostly using Sonnet and Opus, that if a problem instance created discordant behavior, or where one model solved it and the other didn't, between Sonnet and Opus, that increased the eval score for Factory. Also, as a side note, OpenShift was super helpful in this work, allowing us to run all of these different synthesis and eval steps in parallel through thousands of kind of like simultaneous distributed jobs. and with the help of Oleg and Rohan as well, we were able to not only scale the synthesis and kind of problem statement generation, but also validation and evaluation with Harbor. Yes, and definitely to Yi too, and lots of other folks on the team who helped with all of this scaling work. So in terms of the results, I went ahead and looked at both the SWE-Benchify synthetic data set, the SWE-Smith synthetic data set, as well as the mined instances that we got from the first version of SWE-Benchify from like real Go and real Python repos. And so you can see here that basically 16% of SWE-Benchify issues, the LLM as judge classifies as being realistic or likely real issues rather than generated, whereas for SWE-Smith, that's only 1.5% of the samples from their benchmark that fake LLM as judge into believing that they're real issues. There's definitely a lot of daylight still between these synthetic issues on the left and the real issues on the right that are mined from real repositories. But I think that this was a clear step in the right direction, where there's an order of magnitude difference in terms of how many more samples were able to get past judge evasion in SWE-Benchify versus SWE-Smith. In terms of the problem difficulty, again, like I think what I was looking for was more to find problems that created discordant behavior between frontier models and harnesses. I think benchmark problems are not particularly useful in coding agents if they're either too easy or too hard, meaning if all of the models are solving the problem, you don't learn anything. And if none of the models or harnesses can solve the problem, you also can't learn anything. And so I was trying to really maximize this middle row, which is where one of the models that is being tested solves the problem. And we were able to get that to 20% compared to SWE-Smith's 11%. I also included in the right-hand column how these numbers stack up against the real issues mined from Git history from the first version of SWE-Benchify. All of the data sets with both the mined instances and the synthetic instances that have come out of SWE-Benchify are now published to Harbor and ready if anyone wants to play around with them or explore. I think we've been looking for different benchmarks that we can use for proving out different modes for remote factory. I think SWE-Benchify is a really good target for us to look at. So I've talked a lot about evaluation, but I think as important, or maybe even more important than evaluation, is to move from using these problem instances for making decisions about models and harnesses and which ones are stronger and weaker at coding and coding on different in different languages and repositories, to actually doing model training and harness training and optimization. And so I think, you know, the big problem with the big problems that I mentioned at the beginning of my presentation about SWE-Bench, that there's contamination and that a lot of human effort goes into curating these instances. I think we've largely solved these now with a combination of mining and synthetic data generation, and have a good ability to point at an arbitrary Git repository now and generate a large number of problem instances that are realistic to problems that bugs that might come up in the wild in these repositories. And we can use these for tasks like taking open source models like GLM or Quen and seeing if we can train harnesses to match the performance of frontier models specifically for work in these target repositories. In addition, I think we'll continue to work to kind of expand to more programming languages, working to improve the judge evasion towards the baseline from real instances, and in addition, see if we can increase the difficulty of problems that we're generating so that a user of the synthesizer could specify how difficult they want the problems to be, and to have SweetBenchify generate a distribution of programming challenges that will kind of like match different levels according to the needs of your project. And that's what I had to share this morning. Are there any questions or comments for discussion?
There is a question. I have a quick question, Ari. So I wonder, do you also generate like synthetic test case, or do you assume like the GitHub repo already has some test case you can reuse?
Yeah, so importantly, all of the test cases are human written. And that kind of grounds the synthetic issues that we're generating in the realism of the expectations that humans have of the software. And so it's part of the synthetic data generation process is making these mutations and then running this validation to ensure that basically the unit tests go from passing before the change to failing afterwards.
Got it. I have another question. So I think if you go back maybe slides, the table you showed, maybe yeah, this one. So it seems like for Swiss Miss, they're like 34% like that zone. So because I think from your presentation, I had the impression which was, sometimes like the description in the question in Swiss Miss has some hint for the solution. So which means like that would make those tasks very easy to solve. But why is there like a lot of question being in the dead zone?
Yeah, that's a great question. So I did a little bit of qualitative analysis in order to help figure out why it was that 34% of the Swiss Smith problems that I looked at were not solvable by Opus or Sonnet. And I think that like a large number of these might actually be unsolvable. That basically, something that I mentioned in terms of how Swiss Smith does their, they don't have like as strong of a quality gate. Essentially, in order to be included in their data set, it just has to be that the mutation breaks at least one test. And so it might be that that basically there are going to be issues that prevent a model from where essentially like no patch could fix the issue that is being described.
Got it. Yeah, I guess a follow-up question was, I think you mentioned like empirically you observe the synthetic data you generated, like most of them are solvable. But I wonder if there's any maybe evaluation or maybe some way you can include in your pipeline to make sure the question, like kind of do another sanity check to make sure the question is solvable. Because it seems to be a big issue, as you mentioned, for SweetBench. So I wonder, like, if there's any way to, like, kind of check it. I'm not just wondering if you have any thoughts.
Yeah, that's a great question. I think, I mean, the most basic thing we could do is to use LLM as judge to ask, like, is there a reasonable way in which a coding agent could transform this this problem statement into a patch that fixes it? I think like it would be hard. It's hard for me to imagine, and I'm interested if anyone else has ideas here. Like, there's always the solution of, you know, exactly the inverse patch of what mutation was introduced. The only question is, like, is there enough information in the issue that ends up getting generated, conditioned on the patch that got introduced, in order to basically do the reverse engineering? And yeah, I'm not sure off the top of my head if I can think of something other than asking like LLM as judge if there's enough information in the issue to solve the problem.
God, yeah, that makes sense. Yeah, I think it's kind of like a trade-off. Like if you give too much hints in the description, it will make the question super easy. But if you kind of remove some critical information, it may make the question unsolvable.
Right, exactly.
Yeah, are there any other questions?
I have a question too. I'm here, Harry. Like when you show, when you show like this LLM as a judge that can basically to try to understand which one are synthetic data, which one are real, and you show that like Sweetbench Smith is like 1.6, and your method is like 15%, 16%, right?
Yes.
But still, like, and then you mentioned it's still like a large gap. Like, why it's so easy for this judge to understand what is synthetic and what is real? This is the patch, right? You're showing the patch to the system.
You're showing the combination of the issue and the patch.
Yeah. And why do you think it's still like relatively easy for the model to understand what is real and what is synthetic?
Yeah, that's a great question. And I think like something that I can share from the experiments that I ran is that a big step change going from like something that really helped in improving the realism or the judge evasion was coordinating changes over multiple files. Basically, like single file mutations are kind of obvious telltale signs of this was a bug that was synthetically introduced. And so I think that what's most likely going on, and I could collect some summary statistics to help support this argument, is that real PRs tend to touch like a lot of different files and might be like pretty complex. Whereas if you look at typical synthetic problems, it might mutate one or two functions or classes and be really targeted in terms of like they might just be kind of vanilla looking and not capture a lot of the complexity and like difficulty from real human software is sort of the intuition that I have. Oleg?
Yeah, one question is, were you ever able to look at the feature bench thing? Because I think this is the exact problem that they try to solve.
I haven't played around with feature bench, but I would love to dig into it.
Yeah, I think that's something that would be interesting to look at, because they basically look at multiple PRs and issues that touch multiple PRs rather than just like one patch fix.
Yeah, that makes sense, and I think that would definitely go to increase the realism of some of these benchmark problems.
Any other question? I guess if there's no more question, we can thank the speaker again. Maybe we can. We have one more question.
Yeah, I was just wondering where we could find the video, because I know it's recorded.
Yeah, I can
Oh,
send you
no,
the link.
okay, thank you.
Yeah, you can.
Thank you, everyone.
Thank
Thank
you.
you.
Thanks, y'all.